Hi girls and boys, hope you are fine? Right, good. Now in this session we will be primarily discussing on the solubility of substance in liquid, that is we are going to discuss about liquid solutions. Before we start this session, let me tell you what we discussed in the previous 3 sessions. So in first module we discussed about solutions and different type of solutions, and the second module we discussed about different methods to express the concentration of the solution, and in the third module we started discussing the solubility of a gas in a liquid, and related to that we discussed the Henry's law. So I hope you have gone through all those classes and you are clear about whatever we discussed in the previous 3 sessions. Now, so in this class I am going to discuss about a liquid dissolved in another liquid, and we already discussed the dissolution of a gas in a liquid and the various factors affecting it, and related to that we discussed Henry's law, right. Now we are going to discuss about a liquid dissolved in another liquid solution. First we will be focusing on this, and after that we will be discussing a solid dissolved in a liquid. So first we will be focusing on liquids in liquid. Okay. So when I say a liquid, you know in class 11th we already discussed about something called vapor pressure. It is one of the properties of a liquid. So what do you mean by vapor pressure? Just recall what we learned in class 11th. We define vapor pressure as the pressure exerted by the vapors above the liquid surface which is in equilibrium with the liquid at constant temperature. So what is it? I am repeating, it is the pressure exerted by the vapors of a liquid above the liquid surface which is in equilibrium with the liquid at constant temperature. So when I speak about solutions, it can be a liquid dissolved in another liquid, or it can be a solid liquid dissolved in a liquid. So if you consider a liquid solution, first of all you take a pure liquid, let it be your solvent. The vapors of the solvent will exert some pressure. What you call that pressure at constant temperature? Can you call it as vapor pressure of the liquid? Clear? So we can call it as vapor pressure of liquid. Now how to measure this? You can see here, when you keep some water, say you keep some liquid water in a container and it is connected to a pressure gauge. Okay. Now in the beginning you kept only liquid, but after some time what happened? This liquid water starts to evaporate. You can see the vapors of water slowly coming up. Okay. So now this vapor start collecting over the surface of the liquid. This is the liquid. So above the liquid this vapor starts collecting. Now since it is connected to this manometer, you can read the pressure exerted by the vapor. You know, gas molecules, they start moving and they randomly move and collide with the walls of the container and exert pressure. So now this pressure which it exerts in the beginning, can you call it as vapor pressure? No, it is simply the pressure of the vapor. It is not the vapor pressure, it is the pressure of this vapor. Now after some time what happens? You see here only one side process is taking place, that is only evaporation is taking place. After some time the gas molecules which are present above the liquid surface, they slowly starts to come down. So at this stage both evaporation as well as condensation are taking place simultaneously at equal rate. That means if 2 molecules goes into vapor, another 2 molecule from the vapor slowly condense and come down into form of liquid. If you take 100 molecules going into vapor, at the same time 100 molecules of the vapor come down into the liquid. So what is the net change in the number of moles of vapor and in liquid? Will there be any change in the number of moles of the vapor and liquid? It won't change. Or in simple words we can say the system attained a state of dynamic equilibrium. It attained a dynamic equilibrium. So, what is the characteristic of dynamic equilibrium? All the measurable properties of the system will become constant. Clear? So, at this particular time, what is the pressure exerted by this vapor? So, this is the height of the mercury column and you can calculate the pressure, and this pressure is what we call it as vapor pressure. What we call vapor pressure, and this vapor pressure is a constant at a particular temperature. It is a very important thing, because as temperature changes, number of molecules that evaporate will also change. So, at a constant temperature, the vapor pressure of a liquid become constant. So, we will be looking at a solution which is formed by mixing two liquids. So, now you know the concept of vapor pressure. Vapor pressure is for a particular liquid. Now, I am going to mix two liquids so that both the liquids will produce its vapor. In that case, how you will relate it to its vapor pressure and the amount of the liquids that you mix. So, this is what we are going to discuss now. You consider a liquid solution formed by two liquids, one is benzene and another is toluene. Here I have taken certain amount of toluene in a container. Say I have only toluene here, only toluene I have in this container. So, when I keep it for some time, what happens? It starts to evaporate. So, this vapor start collecting over the surface and finally it get into an equilibrium with the liquid. Okay. So, this is the vapor and this is the liquid. So, the evaporation and condensation takes place at simultaneously and same rate, so that the net change will be 0, and the pressure exerted by the vapors above the liquid, that is above this toluene, will be constant, and we call that as the vapor pressure of toluene. Now, you have another liquid, which is the next liquid. I took benzene, I took pure benzene. So, when I take pure benzene and kept inside a container, the same thing happens. It evaporates and finally the vapors and the liquid get into an equilibrium and they get into dynamic equilibrium. Then the pressure of the vapors above that liquid become constant, and you call that pressure. What you call the pressure exerted by this vapor? It is called the vapor pressure of pure benzene. Now, what I am going to do? I am going to mix equal quantity or some other proportion. I am going to add benzene and toluene. So, when I mix benzene and toluene, you know both benzene and toluene can produce its vapors. So, in the solution, so when I mix them, you can see both toluene molecules as well as benzene molecules are there, and these molecules starts to evaporate. Both of them starts to evaporate. The liquid form changes to vapor. So, do you think only benzene will come into vapor or only toluene will come into vapor? No. Both the vapors of toluene and the benzene will be formed in the vapor. Now, individually they get into equilibrium with their respective liquids. This vapor and the liquid get into an equilibrium when both the condensation and the evaporation of the respective components get into an equilibrium. What happens? The total pressure above the liquid, that is, now you have the mixture of the vapors of both toluene as well as benzene are there in the vapor, and both of them starts exerting pressure, right. So, now we have a total pressure. So, what is this total pressure equals to? This is what we actually learned in class 11th using Dalton's law. Do you remember that? What is Dalton's law of partial pressure says? The total pressure of the gases in a mixture will be equal to the sum of the partial pressure of each of the gas component present in the solution, provided they are non-reacting gases. They should not react each other. So, we can apply the same thing here. That means, if I say P total, what is P total? P total is nothing but the total pressure exerted by the vapors above the liquid. It will be equal to the partial pressure of benzene partial pressure of benzene plus what is the next component? Toluene. So, partial pressure of toluene, partial pressure of benzene and partial pressure of toluene. Is it okay up to this? Are you familiar with this person? Who is he? His name is there. His name is Francois Marie Raoult. Marie Raoult studied the relation between the quantity of the liquid and the vapor pressure produced by the liquid, and based on his observation he proposed a law. What is that law? So, that law is called Raoult's law. What we call Raoult's law. Okay. So, what Raoult's law says? It states that for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in the solution. What is it? Please read it again. That is, it states that for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in the solution. Or in simple words I can say, if the quantity of the component present in the solution, if it increases, definitely what will also increase? The corresponding vapor of each component will also increase. Or in other words we can say, if you express the quantity in terms of mole fraction, if the mole fraction of the component present in the solution increase, definitely what will increase? Its vapor pressure will also increase. Clear? Or simply I can say the vapor pressure P of a component in a solution is directly proportional to, they are directly related, right? So, they are directly proportional to chi. What is chi? Chi is nothing but the mole fraction of that component in the solution. Is it clear? This law is called what? Raoult's law. Now, you can equate it, it is only constant, it is only proportionality, right? So, you can equate it. How we will equate it? So, P is equal to, you have multiply with a constant, right? So, chi, which constant I am going to multiply is nothing but P0. What do you mean by P0? P0 is nothing but it is the vapor pressure of pure component. It is the vapor pressure of pure component. Or simply you can write Pi. What is Pi? Pi is the vapor pressure, partial vapor pressure of ith component, partial vapor pressure of ith component, which is equal to Pi0. What is Pi0? It represents the vapor pressure of that pure component into chi I. What is chi I? It is the mole fraction of that component present in the solution. So, we have pressure, partial pressure of a component in a liquid is equal to P0, that is the vapor pressure of that component into chi, that is the mole fraction of that component. Now, imagine you have a binary solution. We already discussed what are binary solution, only two components. So, here I take component 1 and component 2, two components, component 1 and component 2. Now, I can write P1, that is the partial vapor pressure of component 1 is equal to, how can you relate it? It is equal to P10 chi 1. Clear? Now, component 2, P2, the partial vapor pressure of component 2 in the solution is equal to P20 chi 2. Clear? Now, what I am going to do? I know chi 1 plus chi 2 is equal to 1. Chi 1 plus chi 2, that is total, the sum of all mole fractions of the components in the solution will be always unity, it is 1. So, from this can I write chi 1 is equal to 1 minus chi 2? We can write like this. Now, I am going to apply in Dalton's law of partial pressure. So, why now P total is equal to what? It is equal to P1 plus P2, that is the partial pressure of component 1 plus partial pressure of component 2. Now, what is P1? I have P1 equal to what? P10 chi 1 plus what is P2? P2 is P20 Chi2. Clear? Now I have what is Chi1 in terms of Chi2. So I am substituting here P10 into what is Chi1? Chi1 is 1 minus Chi2 plus P20 Chi2. Now I can separate the terms. I can write P10 minus P10 Chi2 plus P20 Chi2, or further I can write it as, so we can take that common term out, that is Chi2 you can take out. So P10 plus P20 minus P10 into Chi2. So what is P total equals? P total is equal to P10 plus P20 minus P10 into Chi2. So now if you look at this equation, it basically represents an equation of a straight line which is of the form y equals mx plus c. Y equal to mx plus c. Here this stands for y, here it is c, and here it is m, and this is x. This is nothing but an equation for a straight line, or here the variable is Chi2. So when you plot a graph by taking total pressure P total against the mole fraction of one of the component, you should get a straight line with y-intercept and slope. You should get a straight line with y-intercept and a slope. So this is the graph that we are going to get. Here you can see we are taking the vapor pressure of component along y-axis and the mole fraction of the component along x-axis. Here I have plotted both the solute and solvent together in it. Here you have component 1 present in the pure form, and here you have component 2 present in the pure form. So when you mix them together at different proportion, it forms a solution. Now from this graph you can see it is a straight line graph. You are getting straight line graph, and what is P total equals? P total is equal to P1 plus P2, where P1 is nothing but the partial vapor pressure of the component 1 and P2 is the partial vapor pressure of component 2. And here you can see what is the maximum value of the vapor pressure obtained when Chi1 equal to 1, that is nothing but P10. What is that P10 called? That P10 is nothing but the vapor pressure of the pure liquid, that is the component 1. And here you can see P02. What is P02? It is the vapor pressure of that component 2 in its pure form. Okay, clear? Now from this graph we can go to certain conclusion. What are the conclusions we can arrive at? We can see the total vapor pressure over the solution can be related to the mole fraction of any one component. So we derive the equation. You can just see this. In this equation we have P total is equal to P10 plus P20 minus P10 into Chi2. What is Chi2? Chi2 is nothing but the mole fraction of component 2. So the total pressure of the solution, total vapor pressure of the solution is related to the mole fraction of one of the components. That is the first thing. Total vapor pressure over the solution can be related to the mole fraction of any one component. That is the first conclusion we can arrive at. What is the second conclusion? The total vapor pressure over the solution varies linearly with the mole fraction of the component 2, because we have expressed the total vapor pressure in terms of Chi2. So as Chi2 changes, the total vapor pressure will also change, and depending on the vapor pressure of the pure component 1 and 2, the total vapor pressure over the solution either decrease or increase with the increase of the mole fraction of the component 1. So what is it? That is, depending on the vapor pressure of the pure components 1 and 2, the total vapor pressure over the solution can either increase or decrease with the increase in the mole fraction of the component 1. So depending on the mole fraction of 1, the pure components, that is P01 and P02, depending on that also it can have a higher value or a lower value. It can either increase or it can decrease. Clear? Now, if you consider the vapor phase, you consider the vapor phase of a solution. Example, you take component 1 and component 2 in the liquid state. Okay. So, it evaporates and it forms the vapors. So, in the vapor stage you have both the components. Which are the two components present in the vapor phase? Component 1 and component 2. Clear? Now, you have the total vapor pressure PT. What is total vapor pressure? As per Dalton's law, it is PT is equal to what? It is equal to the sum of the partial pressures of each component, that is the total vapor pressure. If you know the total vapor pressure, then you can find the individual partial pressure provided. You should also know the mole fraction of each component in the vapor phase. What is it? If you know the mole fraction of each of the component in the vapor phase, I am not saying about the liquid phase, I am saying about the component, the mole fraction of the component in the vapor phase. If you know the mole fraction of the component in the vapor phase and the total pressure of the solution or total vapor pressure of the solution, you can find out what is the individual partial vapor pressures. So, how you can find it out? You can see, you consider Y1 and Y2. What are Y1 and Y2? Let them be the mole fraction of the component 1 and 2 respectively in which phase? Vapor phase. Remember, it is not in the liquid phase, it is in the vapor phase. Then you can apply Dalton's law of partial pressure. How will you apply it? You know that P1, what is P1? It is the partial pressure of the component 1 in the vapor phase. It will be equal to what? The total pressure, that is P total, into the corresponding mole fraction. What is the mole fraction of component 1? Y1 into Y1. Similarly, what is P2 equals? P2 is equal to the total vapor pressure of the solution into Y2. What is Y2? Y2 is the mole fraction of the component 2 in vapor phase. Or generally you can write for any I component or ith component, the total the vapor pressure Pi is equal to what? It is equal to the total vapor pressure of the solution into the mole fraction of ith component in the vapor phase. So, we can simply write it as Pi is equal to, what is Pi equal? Pi equal to Yi into P total. Is it clear to you? Shall we proceed? Okay. Raoult's law as a special case of Henry's law. You know each of these laws very well now. So, what Henry's law says? That is, the amount of the gas that is dissolved in a particular quantity of liquid is directly proportional to the pressure or the partial pressure of the gas above the liquid at constant temperature. So, based on that we derive what is P. What is P equal? P equal Kh into chi, where Kh is called Henry's law constant. We already discussed about it. Now we discuss Raoult's law. So, you can write the equation for Raoult's law. P is equal to P0 chi. This is Raoult's law. So, what is P? It is the partial pressure of the component, the vapor of a component in a solution. P0 is the vapor pressure of the pure solvent or pure component, and chi is the mole fraction of that particular component in the solution. Now, if you compare these two equations, both Henry's law and Raoult's law deals with partial pressure and its relation with the mole fraction. The only difference here, one is related to a gas dissolved in a liquid and another is related to the vapor pressure of a liquid. Now, you can see both are partial pressures, both are mole fraction. So, this can be equated. When it can become equal? It can become equal when Kh is equal to P0. What is Kh? Kh is nothing but Henry's constant for a particular gas. And what is P0? P0 is nothing but the vapor pressure of a particular liquid. So, when this become equal, we can say Henry's law and Raoult's law are same. Or you can treat it like this. You imagine you have a liquid with very high volatility. Very high volatility in the sense it is behaving almost like a gas. In that case, both Henry's law and Raoult's law become same, or simply we can say Raoult's law is only a special case of Henry's law. Next we will be discussing about a solution formed by dissolving a solid in a liquid. We are going to discuss about a solution formed by dissolving a solid in a liquid. Now imagine solid. So many solids we dissolve in water or in liquids. Example, glucose dissolved in water, salt dissolved in water. Anything that is soluble in another, any solid that is dissolved in another liquid forms a solution. Now the question comes, if you take pure liquid, you keep it for some time, can it produce its vapor and finally gives you the vapor pressure? So what do you call that vapor pressure? It is simply the vapor pressure of the pure liquid, nothing else. Okay. Now we are going to make into a solution by adding a particular amount of solute to it. Which solute I am going to add? Yes, I am going to add a solid solute to it. So when I add a solid solute, look at the nature of that solid solute. Is it an volatile solid or a non-volatile solid? If it is a non-volatile solute, definitely it will create some impact on the vapor pressure of the liquid. That is what we are going to discuss now. You can look at this figure. Here I took some liquid in a container and kept it in a closed environment. Now you know what happens. This liquid starts to evaporate. So this liquid starts to evaporate and it starts collecting above the surface of the liquid, and if you keep the temperature to a constant level, this vapors which collects above the liquid will exert pressure. That is what we call it as the vapor pressure of that liquid. Now I am going to make into a solution. How I can make into a solution? So by adding a solute. Which solute we are discussing about? Solid solutes. Which kind of solid solute? Non-volatile solutes. So when I add a non-volatile solid solute into that liquid, I will get a solution. So if you look at the pressure of this solution, you will see that it will be only due to the partial pressure of the solvent, because the solute is a non-volatile solute. It is not going to generate any vapor. So the total pressure of this solution, total vapor pressure of this solution is only due to the pressure of the vapors of that liquid. But if you look at its magnitude, you can see that its vapor pressure is lowered. Its vapor pressure is lowered. When compared to its pure liquid, the solution, once you made into solution, its vapor pressure will be lowered. So what is the reason for this lowering of vapor pressure? Now if you look at this picture, you can see that you compare these two pictures. Here you can see, here you have the surface occupied by only one kind of molecule. Which is that? That is the solvent molecules. So the entire surface is available for evaporation, for the formation of vapor. But now once I add a solute into the solvent, it forms a solution. Once it forms solution, you can see some of the surface get occupied by the molecules of solute which is non-volatile, So this in effect decrease the effective surface area from which the evaporation takes place. Is it clear? That is, the addition of a non-volatile solute to a solvent in effect decreases the effective surface area from which evaporation takes place. Consequently, the vapor pressure will also decrease. This is the reason why when you add a non-volatile solute to a solvent, the vapor pressure of the liquid decreases. Is it okay? Clear? Okay. Now, you can state the same Raoult's law in a different form. How we can state the same Raoult's law in a different form? You can say, for any solution, the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. What it says? For any solution, the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction in solution. That is, if you have a more volatile component and that volatile component is present in larger quantity, its mole fraction in the solution is quite large, definitely the vapor pressure of that component will also be large. Clear? And you can say that P1, what is P1? It is the partial pressure of the component in a solution. It is directly proportional to Chi1. What is Chi1? Chi1 is the mole fraction of component 1 in the liquid solution into P0. What is P0? P0 is the vapor pressure of that component. So, from this we can say P1 is directly proportional to Chi1. P1 is directly proportional to Chi1. So, when we plot a graph by taking the vapor pressure along y axis and the mole fraction, that is chi, of the solvent, because here only the solvent is the volatile component, the solute is non-volatile. So, if you plot the vapor pressure along y axis and mole fraction of the solvent along x axis, you will get a straight line which passes through the origin. So, this is the graph that you get for plotting this equation. So, children, I am going to wind up this session today. Actually, we discussed about a solution formed by dissolving a liquid in another liquid, and we also discussed a solution formed by dissolving a solid in a liquid. And related to that, we discussed about Raoult's law, and we saw Raoult's law is a special case of Henry's law. So, I hope you understood what we discussed in this module. So, in the next module, we will be discussing about ideal solutions and non-ideal solutions. Thank you.